Okay, so let's go ahead and get started. So I think homework 5.5 was still being graded at the time I made my announcement slide, but homework 5.4 was, and everybody got their grades for exam 2. Again, my apologies for taking a little bit more time than I would have liked to get the grades to you, but I think you all did very well. Again, my apologies for having to pre-record the lecture on Monday. I really didn't want to do that, but it was just sort of like unavoidable for me. How did trusses go? Is everybody shaking your head no? Let me say this. Would it be worth it to go through the example in class again? Were there any specific questions that you had on the homework? Because if we need to adjust some things with the homework, we can. I want to make sure I'm answering your questions, especially given the fact that we took the day off, or kind of took the day off on Monday. How did the homework go? I mean, let me just point blank ask. Okay, I'm getting some thumbs up, I'm getting some of this. Is there a specific part on the homework that was like, okay, I don't know what I'm doing here?
I felt like when I was like going through the entire truss, like I was just kind of like, wait, like
no, it's okay. I mean,
if I was like doing it right, I guess.
That's fair. That's fair. I tell you what. I think what we can do is I think I'm going to call an audible right now. Yeah, I think I'm going to call an audible right now. This is what I'm going to do. I'm going to make homework 6.2 a bonus assignment, so you don't have to do it if you don't want to. And what if we spent at least the first part of today going through this? And I'll do you one better. I will take homework 6.1, and if anybody wants to resubmit up through Friday. Y'all want to do that? Mm-hmm. Is that fair? That way I'm not, doing that. Okay, so is that good? Okay, now, so I want to take a few minutes and go through joints stuff. So what I'm going to do, here's what I'm going to do. I'm going to start with like the example, and I'm going to take it one step at a time, and then maybe we'll get specific about the homework, because what I want to make sure is that what I explained in my video made sense. Okay? So the first thing is that we did in the example problem on the video is compute the reactions. Is there anything about this part of the problem that was just, I don't know what I'm doing? Was this part easy? I mean, tell me. I mean, don't hesitate. If this part was confusing, you tell me. I'm going to assume everybody's good. Everybody good? Okay. All right. So I think the next thing that probably would be valid is to spend some time looking at this. Okay? Because I think if you understand how to analyze one joint, you can do them all. Okay? Yes?
I thought of a question for
yeah.
Like some of the forces of X direction, why is there's one going like CX, why is it 0? Like if you go up some.
Sorry. Oh, the CX is 0. Because if you look at the original structure, there are no forces going this way. The only forces are vertical, right? So here's what I propose. There's an unknown here, an unknown here, and an unknown here, as there would be in any structure. Okay? But if I look at the known quantities, all I've got is vertical and vertical. So, I mean, if you were to write the equation, I mean, just think about it. Summing forces in the x direction and writing every force to the right is positive. The only force I have is that. So it's got to be 0. That's what I'm saying there. Does that make sense? Okay. All right, let's go through this joint analysis. Let's see if anybody has any question about the reactions. Okay. So let's go through this joint analysis. Okay, so the first thing that I want to ask is does everybody understand why I started this example with joint C? In other words, could I have started with joint E? Okay, remember that whenever you do a joint analysis, you must start with a member that has no more than 2 unknowns. So if I start the problem at joint E, I have 1, 2, 3 unknowns. 1 unknown for every member. I can't start at E. I'm not saying I can't analyze E at some point, I just can't start with it. So there are only 2 joints I can start with, C and what? A, right? Would you like to do A off to the side? Just because? We can just do A. Let's just do it on the fly just to make sure we're familiar with it. Okay. So I'll do it here on the board. Okay. So here's how it works. Okay. So here's joint A. Okay. So the first thing I'll do is I'll put the joint here and I'll put all the members framing into that joint. So there's only 2 members framing into joint A. Okay? So far so good? All right. Now, the next thing I'm going to do is I'm going to put a little slope ratio there to indicate that the member is, what the slope is on that member. Okay? And the next thing I'm going to do is I'm going to put the actual loads that are applied here of 2,000 pounds. Okay. Everybody with me on that? All right, sound good? Okay, now we need to deal with our unknowns. Okay? Now I propose that when you first start doing a joint analysis, if you don't know what to do, just assume the force is in tension. So in other words, I'm going to have an unknown like this, and we'll have an unknown like that, okay? Now I'm going to do something with this diagonal here in a bit, but bear with me. So we'll call this unknown here FAB, okay? And I'm going to call this FAD. And I'm calling it AB because it's member AB, member AD. All right? Sound good? Okay. All right. Now, my apologies, but I'm going to take this and I'm going to replace it with this and that. So we'll call this FADX, FADY. Okay? So the idea is like if I have a diagonal, right? They've either both got to be pointing away or they both have to be pointing towards, right? They're either both in tension or they're both in compression. Does that make sense? Both contributing the same way. Okay. Now, the reason I do this is because, here are my equations of equilibrium. Those are my equations of equilibrium. So it would be natural to just write this in terms of x and y. So write this in terms of x, this in terms of y, so I can look at it accordingly. Okay. So far so good? All right. Now let's just be very basic about this. Everything in red is a known quantity. Everything in blue is an unknown quantity. How many blue arrows do I have along the x-axis? 2. How many blue arrows do I have along the y-axis? 1. Okay? So what I'm going to do, if you don't mind, I'm going to erase this. So what I'm going to do is I'm going to sum forces in the y direction first. Okay. So I've got negative 2,000 pounds minus FADY equals 0. Is everybody okay with that? So therefore, that's going to be negative 2,000 pounds. Or another way of interpreting it is you could say 2,000 pounds up. Now, why am I doing that? Because when I drew this arrow going downward, I made an assumption that that's the way it's going to behave, and I was wrong. And I was wrong because my answer was negative. Everybody okay with that? Okay.
So does that mean your ADX is wrong as well?
Yes, that you stole my question. You're 100% right. So if you want to maybe, I don't know, redraw the joint down here. So here's the 2,000. And if you want just sort of a little record of what's going on, so this is 2,000 going up, okay? I mean, now does that make sense vertically? 2,000 pounds down, 2,000 pounds up, got to be 0, right? Okay. All right. Now, whenever you are dealing with a diagonal, if you get the vertical, immediately solve for the horizontal, or vice versa, okay? So how do I do this? This is how I do it, okay? I keep this really simple. Okay, so I propose that 2,000 pounds is to the 8 as whatever this is to the 6. And I guess I should say negative to use the equation here. So what I'm basically saying is that this vertical component corresponds to this vertical number, this horizontal component corresponds to this horizontal number. Very simple way of dealing with the trig. So therefore, FADX is negative 2,000 pounds, 6/8, or 1,500. So if you want to redraw it, we're basically saying that. Is everybody with me on that? Okay. Now, if this is 1,500 pounds this way, what's that? 1,500 pounds this way. So what I'm getting at, this is what I'm getting at. I'm saying that FAB is indeed going to be positive, or in tension, and then FAD just use Pythagorean theorem, okay? And when you use Pythagorean theorem, you're going to get that, but it's going to be compression. That's it, okay? And what I'm saying from there, this is what I'm saying from there, is here's this. Just do it for the rest of the structure, right? So I started here. So I did joint C first, then I did joint A, and here's joint A, so I did it the same way here, right? Then I said, okay, if I look at joint D has 3 members framing into it, but I knew one of them going in. So then do joint D, then do joint E, and then the very last joint you ended up having to do, because if you follow all your forces, you already knew what they all were. Does that make sense?
So for AB, when you're finding like so it's 1,500 pounds in tension?
Yes. Okay, and so let me guess. Is the question, why did the arrow flip?
Yeah.
What's your question?
Okay, I thought when they were facing each other, that's compression.
They are. What I'm saying is, here's the joint.
Okay.
The force is pulling away from the joint. If you're the joint and I'm pulling 1,500 pounds this way, that's tension. So the force is going away from A. These two forces are going towards A, so that's compression.
So, but for AB.
This is AB, right?
Yeah.
Yeah. Okay. No, go ahead.
I don't even know what to go ahead with.
The 1,500 pounds is going away from the joint.
Okay. So if it's going away from the joint, it's tension.
Yes.
Okay. I guess when the arrows pointed towards each other from either joint.
You're saying like this and this? Is
Yeah,
that what you're getting? Okay,
Okay.
no. This is what I'm saying. I'm saying that both, okay, this is going away from the joint. This is going away from the joint. I'm saying that the forces are always going to be equal and opposite. Okay, let me put it to you this way. Okay, all right. What we are recording is the internal response, not the external response. That's what's going on here. Here's the marker, okay? Watch my hands. My hands are applying compression. So this hand's going that way, this hand's going that way, right? So compression. But my hand is being resisted. The marker is pushing the other way. Do you see what I mean? So what I'm saying is, if you have a member and you yank on it with tension, right? The member responds the other way. The member responds by wanting to pull back. Think about it like this. If you had a rubber band and you pulled on it, what's the rubber band want to do? Right? So if member AB is a rubber band and you yank on it, that's what member AB is wanting to do, is snap it back the other way.
Oh, that
Did that clear it up for everybody? I'm just saying compression is the exact opposite. If you were to push on a spring, the spring wants to do that.
But on line AB, you still write that it's compression, right?
No, that's tension. So this is what I'm saying. Okay. This 1,500 pounds is not what we're doing externally to the structure. The 1,500 pounds is what the structure is responding with, okay? So what I'm saying is, this is what tension means. If you have a rubber band in your hand and you yank on it, right? You are applying tension. But what is the rubber band doing to you? It's doing that, right? I'm saying this 1,500 pounds, that's what the rubber band is doing to you. It's trying to suck back in. It is responding the other way. That's why it's tension, okay? And so the simple mnemonic is just, if you have a joint and you have the arrow pointing away from the joint, it's tension, and that's why. Did that make sense? How about everybody else? Did that clear it up? Okay, I want to get to some section work today, so let me let's keep going. Any other questions about this example? Yes?
So how do you cancel out the 10,000 on E?
What do you mean cancel out?
Like, it has to have the opposite reaction.
That's a great question. So when you get to joint E, everything in red is what you already knew. You have 10,000 going up, 7,000 going down. This is 3,000 going down. So you have 10,000 going down, 10,000 going up. It cancels out.
Okay, and then what about like 3,000 going that way?
Okay. What 3,000? This 3,000. 3,000 going this way, 2,250 going this way, 5,250 going that way. The cool thing about this joint, here's the cool thing about this joint. When you do this joint, this is like one of the last ones that you do, you have a vertical and a horizontal. That's the only one that you do, or the only ones that you have. So if you treat them independently, as independent problems, you get 3,000 here and 2,250 here, right? Because you'll say, okay, I've got 10,000 up, 7,000 down, I need another 3,000 down. And then you say horizontally, I got 5,250 to the left, 3,000 to the right, so I need another 2,250 to the right. Then, take a look at what you get here. You get two vectors that are pointing the right way. Like, what you don't have is like this going down and that going like that. That wouldn't make sense, right? But take this and divide it by that, and you get 6/8, which is the slope ratio. So it's a check that everything worked out. Does that make sense? How about everybody else?
Will you just like really quick scroll down to like that final image you have?
Yes.
Okay, that was what I was confused about. Is the AB supposed to be 1,500, not 5,250 in tension?
Yes.
Okay. Thanks. I was like
Whoops.
really confused there.
You're right.
Okay.
That's what happens when you do the problem too fast. Yes. Whoops. We'll add like a 0.75 to the mistake count for that one. That one's a pretty high mistake. But yes, that should be 1,500. How are we doing on this? Any questions? So, okay, with this, were there any specific questions about the homework that didn't make sense? Like Were there things about the homework that like, okay, yeah, I get all this, and then I looked at the homework, now I still don't understand what's going on. Yes?
So on the homework, did you want us to get every single joint?
Yeah, I think so. Isn't that what the problem said? Yeah. But the one thing to keep in mind is that I would really try and draw it like this, like in this exploded view, because you can do it really fast. Yes.
I think just like the most helpful thing is just seeing the solution for the homework. Just, I know we'll get it, but like.
All right. Here's what I will do. This is the last thing I'll do. Because I've done a few. I will go on Teams and I will post a couple of the internal forces. Not posting all of them.
Oh yeah, I forgot it's okay.
Because you've got till Friday. I'm gonna open it up till Friday. So like what I'll do is I'll say, like I might give you one reaction and I might give you two of these. So that you'll have something to go off of. Is that fair? Well, I'm not doing any more. Are we good? Okay, any questions on this? Any other questions on the homework? Because I do want to say a few words about sections. Going once, going twice. Okay. All right, let me say a few words about sections. And again, we're going to treat this as a bonus assignment anyways in here. And I want to, so I'll say a few things about it. Let me go to my lecture notes here. Okay, so the thing about sections, about truss analysis using the method of sections is, I mentioned this in the video, but I'll sort of say it in here. When we're analyzing a truss, we analyze it such that ultimately what we're trying to get to, like the three assumptions that we make, is that each member only carries one internal force. It's either a tension or a compression or it's zero, but it's only one value inside the member. Okay, that's what these assumptions basically are distilling the analysis to. Now I told you that there were two methods: a method of joints and the method of sections. Okay, I teach structural analysis, which for all intents and purposes, a lot of that class can sort of be thought of as statics 2 in terms of what we cover in there. So we do truss analysis again, and we go much more in depth. When I cover that topic, we primarily cover the method of joints. The reason why is because I don't know many structural engineers who are designing trusses, and I gave you different examples of trusses in other disciplines, but I don't know anybody that's designing a truss that only wants the forces in a couple members. Ultimately, they need the force in every member to be able to select members. So the method of joints is really the more widely applicable one because you need every answer, okay? The method of sections is really more of a spot check approach. Now, there is an added benefit with the method of sections that you don't get with the method of joints. So when we do a joint analysis, we only have two equations of equilibrium, a sum of forces in the x direction and a sum of forces in the y direction. How come? Like, why are we only limited to those two equations? Because we have all the forces all meeting at a common point, right? All the forces are meeting at a common point. There's no moments. So because there's no moments, we don't have that equation, okay? So one of the tedious aspects of a joint analysis is that we can only do joints with two unknowns at a time. So if you got a really big truss and you got the method of joints, you're going to be there a while, right? It's just the truth. What if I gave you this problem and I said, give me the force in member CD? And that's all I wanted. On method of joints, you can do it, but it'd take you a while. The method of sections will permit you to get that one force fast. So the method of sections is a spot check type approach, okay? I'm going to show you how the method of sections works real quick with this example. And if you'll permit me, okay, given that we've spent some time in here today revisiting the method of joints, what I'm going to do for this problem so that we can get some work done on the method of sections is I am going to go ahead and just give you the reactions. So this is okay. Okay. So normally what we would do is just, okay, some moments at B and some forces in the X direction and all that. Is it okay that I'm just giving you these for the purposes of this in-class example for the method of sections? Nothing about the computation of the support reactions differs here, right? So like, for example, if I'm summing forces in the X direction, I have 16 to the right, I need 16 to the left. And then some moments here, some moments there, so on and so forth. Okay. All right. Everybody with me so far? Okay. Now, with that, let's read the problem. So the problem is saying that we need to determine the internal forces in the following members. Okay? So we need to determine EG, FG, and FH. Okay? So I highlighted them here. Those are the three members that we need to analyze. And in order to do that, we're going to apply the method of sections. Okay, so what is the method of sections? All right. So what we're going to be doing is breaking out the secret weapon of structural engineering, which is the samurai sword or lightsaber, if you happen to be a sci-fi fan. And we're going to slice this structure in half. Okay. Now, let me explain the methodology, the idea behind this. If I'm sitting on this table, okay, and Mr. Schrey has the samurai sword or lightsaber, which one? Lightsaber, okay, good choice. So I'm sitting right here, and Mr. Schrey slices through here with the lightsaber. What happens to me? If I'm sitting on the table and he slices through here with the lightsaber, I fall down, right? What happens to his grade? Okay. All right. The point is that the structure is no longer in equilibrium, right? But the idea of a section cut is it is a thought experiment, right? The idea is if we cut a section, what are the forces required to keep the structure in equilibrium? And those forces would be the internal forces in this structure that I'm interested in. Is everybody with me on that? Okay. So what I'm going to do is I'm going to lightsaber right through the structure right there. Okay. Now, to be blunt, it does not matter which direction that you look. You can look to the left or look to the right. But we are essentially breaking this truss up into two different pieces. Now, you can only cut through no more than 3 bars, than 3 truss members. Why 3? Because I only have 3 equations of equilibrium, okay? Or maybe a better way of saying it, I can only cut through 3 unknowns, right? So you could cut through 7 members, but you have to know 4 of them before you did it, okay? And that just sounds like a really painful problem, and I wouldn't do that to you. Okay, so we're going to cut a section. And we're going to look left. And when I say look left, what I mean is I'm going to cut the section into 2 pieces, or cut the truss into 2 pieces, and I'm only looking at this part. Okay, I'm not looking at this part. So I'm going to look at this. So my apologies for the extra art, but I'm going to redraw this again. Okay, so here's what we've got. We've got, and I'm going to draw it kind of big. Okay. Okay. And you'll see what I'm doing here in a second. Okay. So we'll call this joint A, call this joint C, call this joint E, and then B, D, F. And we'll put G right there. We'll put an H right here. Okay. All right. So the other thing I'm going to do is I'm going to draw the forces that are on the structure on this side that I know. So this is 28 kips. Maybe I'll lower this just a little bit. Okay. And then we have a force here, which is 23 kips. And then a force there, 16 kips. And just to make sure we don't forget our dimensions, sorry, wrong one. This is 10 feet, and each of these are 8 feet. Okay. All right. And you'll see why I drew these over here. Okay? You'll see why I drew these here in a minute. Okay. Everybody with me so far? So this would be what the structure would look like after we took the samurai sword or lightsaber to it. Is everybody with me on that? Now, again, if I'm sitting here on the truss and we cut the structure in half, structure's going to fall down because it's not in equilibrium, right? So, here's what I propose. All right, and I'm going to do this just to sort of make the point. Again, the structure isn't out here, but let's just do that. I propose that there's an unknown force right here. We'll call it FEG. I propose there's an unknown force right here. And I propose that there's an unknown force in this diagonal member, right? I'm going to split it up into X and Y. Like that. But that's what the structure is going to look like. Is everybody with me on that? Okay. A lot going on, but it's actually pretty manageable. Now, okay. The purpose of the method of sections is to do spot checking. But one of the added advantages of the method of sections is that we now can sum moments. Okay? Everybody with me on that? Now, remember when we first started to do equilibrium problems and we said, okay, what we need to do is we need to select where we're summing moments from, and let's be strategic about it, right? Like when we have a beam, right? Why do we sum moments at the support? Because one of the reactions goes right through it, right? So we can ignore that one and solve for the other one, right? Okay, so let me ask you a question, okay? And maybe what I'll do is ask it this way, just to sort of make the point that really what we have is this. About which point do you think it would be a good place to sum moments to eliminate as many unknowns as possible? What's that? F. Let's sum moments here. Because if I sum moments there, I am not considering this, I am not considering this, and all I have is one unknown. Does everybody see that? Now, to be clear, right? Right. Really what I've got, or what I had drawn earlier was this, but it's the same thing. By the way, is there another point that we could sum moments and get the same effect of eliminating two unknowns? Again, structure doesn't care where we sum the moments. We can sum them anywhere. How about point G? We could sum moments at G, no moment due to that, no moment due to that, and just solve for FH. Doesn't matter. We don't have to sum the moments on the structure. We can sum the moments in Albuquerque if we want. It doesn't matter. We can sum them anywhere. Okay? So, but I'm going to sum moments at F. All right? I think that's the nicest moment symbol I've ever drawn. I'll never draw one that nice ever again. Okay. So we are summing moments at F. We do it the same way we've done any problem. Does the 16 kips right here generate moment at F? You're shaking your head no. Why?
Huh?
You shook your head no. Why? I'm asking. You're right, but I'm asking you to tell me why.
I'm on the spot.
It's okay. It's okay. The 16 kips, does that line of action pass through F? Yes. So if it passes through F, does it generate any moment at F? No, right? So do we have to deal with the 16 kips? No. Does the 23 kips generate moment at F? This 23 kips here. Is it positive or negative? What's the moment arm from F? 16 feet, okay? So do I need to consider the 28 kips?
Yeah.
Positive or negative moment? Positive. What's the moment arm from F? 8 feet. Does everybody see what I'm doing here? All right. Do I need to consider any of these? What about FEG? Does it generate moment at F? What, positive or negative? Negative. Times a moment arm of 10 feet. Does everybody see what I'm doing? This is the method of sections, by the way. This is it, right? This is it in a nutshell. So, what do we have? We have, this is 368, or negative 368, plus 28 times 8 is 224. And then just bring that over. This is just algebra. So, there's that. Does everybody see what I did? So member EG is 14.4 kips in what? Compression. Okay. Is everybody following me on this? Okay. So here's my point. From here on, this is really no different than a method of joints problem. So if I know this, how many vertical unknowns do I have? How many vertical unknowns do I have? Okay. So why don't we sum forces in the y direction? So what do I have? 23 kips minus 28 kips plus FEG or FGY. So what's FGY going to be? 5 kips? Now what do I do? Help me out. What do I do? Using the slope ratio, right? So we'll say slope ratio. That's going to be, all these members are 8 to 10. So that is to 8 as, right? So you see what I'm doing? Is everybody like following me? I want to make sure that this isn't too confusing. Everybody with me? In the back? Everybody over here? Everybody up here? So what would be left in this case? Right? Because, I mean, think what I have. Let's just start writing down what we know. This is negative 14.4. This is 5 kips. This is 4 kips. What am I left with? I'm left with FH, right? And how would I solve for it? Say again? In the x direction, right? So I'll do that. I don't want to get away from the screen here, so I'll put it here in the notebook. But some forces in the x direction. So we'll say forces to the right are positive. So I've got negative 16 kips. I've got, this is to the left, so minus 14.4 kips, plus 4 kips, plus FFH equals 0, right? So that and that is negative 30.4, that's negative 26.4, plus FFH equals 0. See what I'm doing? Is that challenging? You tell me. I think if you understand the method of joints, the method of sections is pretty easy to figure out. Okay. We were on the fly today. I kind of liked it. Any questions? Yes?
So that's tension?
This one will be tension, yes. It looks like, yeah, that one will be tension, this one's tension, that one's compression. Because, so the way that I handled that is let's just assume anything's in tension, and if we ever get a negative answer, it's in compression. So, if you'll notice on the method of joints problems, that's what I did starting out, and then as I started doing the joints, you could see, okay, that arrow's got to go up, that arrow's got to go down, and you could sort of eyeball it. When you don't know, I just assume everything's tension, and when it's negative, it's compression. Everybody good? All right, I'm going to pull up the QR code, and then I will see you all. Sorry for keeping you over a couple minutes.